Hello, Roman, and welcome back to the series of videos Neural Networks from Scratch in Golang, where we dive into the bare bones of what is the neural network is, and we implementing everything with the Golang, like all of the neurons, forward path, backward path, loss calculation, and so on. And in the previous video, I spent some time to clean up the code and actually fix the mistakes that I made, because previously, well, the chapter that we had before forced us to implement the backward path for the dense layer and for the relu activation function, so we can go back and calculate the impact that each parameter has on the final value. And for example, from the small model that we created before, we have, for example, one layer with the activation relu function, we have the second one, but with the softmax activation function, then we have the categorical cross entropy loss, and as a result we have the loss value and the accuracy. And I think the same we have for another example with a simple model, right? And so, for example, in order to backtrack this model back from the loss to the inputs, we need to create the backward path for the softmax activation function, right? We have forward and for categorical cross entropy loss. And I believe this is what we're going to do next. Let me check a couple of things. Okay, so the first thing that we're going to implement is a categorical cross entropy loss derivative, and I think this is this one, right? Yes. So let's go. If you're not interested in mathematical derivation of categorical cross entropy loss, feel free to skip to the code implementation, as derivatives are known for common loss functions and you won't necessarily need to know how to solve them. It is a good exercise if you plan to create custom loss functions, though I will still go and try to understand the math behind this. Let's go. As we learned in chapter 5, the categorical cross entropy loss functions formula is loss is the minus 1 multiplied by logarithm from y e k, where k is an index of the true probability. So we're calculating the logarithm value from the probability of the concrete class. So for example, when we have the forward pass, in the end we will have a pair of, we will know which category should be the result category, and after the forward pass we will have the prediction of this class, and then we can calculate the loss value, kinda how wrong the model is for this particular one, and that will be this formula, where L E denotes sample loss value, is its sample in the set, and K index of the target label, ground true label, Y target values, and Y hat predicted values. This formula is convenient when calculating the loss value itself, as all we need is the output of the softmax activation function at the index of the correct class. Let's remember what the softmax does. Well, the softmax kind of distributes the values between 0 and 1, and in the end we will have the probabilities of each class. For the purpose of derivative calculation, we will use the full equation mentioned back in the chapter 5. So this is the full formula, but yeah, it got shrink for the specific case into this one. Well, L denotes the sample loss value, so sample in the set, J label output index, Y target values, and Y head predicted. Yeah. For example, the target values in our case will be one value because, well, when we know the concrete class, we can set the known probability. Let's put it like this. Known probability is 100%. And then we have the predicted probability, which is Y hat. But since this is the one value, then we can ignore it. And we can remove the sum because the rest of classes, the target values will be zeros. And this is how we end up with this formula. We'll use this function because our current goal is to calculate the gradient, which is composed of the partial derivatives of the loss function with respect to each of its inputs. This means that we cannot use the equation which takes just the value at the index of the correct class. To calculate partial derivatives with respect to each of the inputs, we need an equation that takes all of them. To calculate partial derivatives with respect to each input, we need an equation that takes all of them as parameters, thus the choice to use the full equation. Okay, so we have d loss over the d. So this is the gradient equation. We define the equation here as partial derivative of the loss function with respect to each of its inputs. We already rounded the derivative of the sum equals the sum of derivatives. We also round that we can move constants. An example is the target values, as it is not what we are calculating the derivative with respect to. Let's apply this transform. So this is the constant values. We have sum predicted values as a constant values multiplied by the derivative from the logarithm. Now we have to solve the derivative of the logarithmic function, which is reciprocal of its parameters. Multiply it using the chain rule by the partial derivative of this parameter using prime, also called Lagrange's notation. Now we have to solve the derivative of the logarithmic function, which is reciprocal of its parameter multiplied by the partial derivative of this param, using the prime, also called the Lagrange notation. Okay. Oh, yeah. This is 1 divided by the function inside the logarithm multiplied by derivative of this function. We can solve it further using Leibniz notation. In this case, we have a function that is logarithm from x, and we have d over dx from this function. In this case, it's a logarithm. So we have 1 divided by the expression inside the logarithm multiplied by the derivative from this function. In our case, it will be 1 because dx over dx is just 1, and this is how we end it in derivative from the logarithm is 1 divided by the expression inside the logarithm. Let's apply this derivative to our sum. So we have this one, and we're changing this part, right? So if we're taking the logarithm by this value, then we have 1 divided by this function or this value, which is this part, and then we calculating the derivative of the function inside by this value. So in our case it will be 1. All derivative of a value with respect to this value equals 1. This is what we have, and then it leads to the derivative. In our case will be a sum of target values divided by the predicted values. Since we are calculating the partial derivative with respect to the y given j, the sum is being performed over a single element can be omitted. Since we are calculating the partial derivative with respect to the given j, the sum is being performed over a single element can be omitted. The derivative of this loss function with respect to its inputs, predicted values on the ith sample, since we're interested in the gradient, then because the rest target values will be zeros except the one particular class. The derivative of this loss function with respect to its inputs equals negative ground truth vector divided by negative ground truth vector divided by the vector of predicted values, which is also the output vector of the softmax activation. Yes, I was just confused with which is also the output vector of the softmax. Yeah, so we have, for example, the categorical cross entropy loss, which takes the softmax activation output. Since we derived this equation and have found that it solves to a simple division operation of two values, we know that with numpy we can extend this operation to the sample-wise vectors of ground truth and predicted values, so further to the batch-wise arrays of them. From the coding perspective, we need to add a backtrack method to the loss category cross entropy loss class. We need to pass the array of predictions and the array of the true values into it and calculate the negated division. Okay, so let's try to. I think this is the one. I did not implement it for the how it's called hot potted. There are two ways to define the target classes. The first one is just for every set of the input values we will have one value, and this is what I have here. It means that for example, I have pair of values like 1, 2, and the predicted class should be first. So in my case I will have it as one value, but the opposite could be, for example, if we have 3 classes, it will be like this. So it means that on which index we have value of 1, those index represents the target class. And so I have this way of encoding, right? So then we're going to, for example, this condition will be relevant for me. But let's do it. So we have the D inputs. Yes. I will try to write in the same way, but I think it will be a little bit different. So we have D values. So we need the number of samples and we need number of values. So it will be samples count and labels. We're taking it from value. Number of labels in every sample. Yes, one hot vector. Labels count. Well, it's basically the values dimensions in my case. Second, I have targets. So I need to create by true and p I. Return two-dimensional array with ones on the diagonal and zeros elsewhere. On the partial derivative calculation by performing two additional steps. First, we are turning numerical labels into one-hot encoded vectors. Prior to this, we need to check how many dimensions y-true consist of. If the shape of labels returns a single dimension, if the shape of labels returns single, which means that they are shaped like a list and not like an array, they consist of discrete numbers and need to be converted to a list of one-hot encoded vectors, a two-dimensional array. If that's the case, we need to turn them into one-hot encoded vectors. We'll use the numpy I method, which, given a number n, returns a square matrix filled with ones on the diagonals and zeros elsewhere, for example. Okay. We can then index this table with the numerical label to get the one-hot encoded vector that represents it. The only thing I don't understand what's... Okay, let's make... I will use the same, but it will be... Right, and I think I already created somewhere. No? Make. Okay. Make by labels count, and then for range true. Make not zero, again labels count, and ideally I can do this range by if y equal to j else well, this is the creation of the diagonal matrix, but I'm still trying to understand what exactly this one does. No? The y true is 1 to 0, but it's actually like this. Then labels equals to 4, right? And then we I labels for example, in this case, we have 3 100 samples, 100 by each class. And the d values on cross and categorical cross entropy loss, we will take the d values from the result, right? So I think this one condense to output. Okay, so in my case that should be 100 by 3. Duration to output print this is one simple model. Okay, so the labels in this case will be 3. So I mean, okay, they should have the same size. For example, wait. Okay, so for example, we have one. We have labels. We have 4 labels. Okay. So what should be the result? We should convert the... Okay, actually, in my case, the labels value is 3. 3 classes. I have 3 classes, and then I need to well, basically... Okay, so I have the metrics, right? The metrics... what is the shape in the end? So it's actually a little bit different. So, I mean, well, the numpy magic makes some things easier. So we actually have the samples count, and then we have the labels count. And, well, first we assume that samples count equals to target to len target, and I think I can do if samples count doesn't equal to len of target, then I can panic with mismatch between target classes for samples for put samples and samples count. So we assume that the target, and for example, if we have 300 input samples, then we provide 300 labels. Oh, if they're not the same, then it's incorrect. Then what we should do instead, actually we can can I fill? No, make. Okay, then for range, if j equals to target y, then we set in to 1, else that should be 0, right? So in the target we will have the target index, and okay, that should be the case. Okay, then we've done with this one, then we should calculate the gradients. And how it works, we go through all of the values and all of the, so they have the same size, they have the same length, and then we divide all of the values, right? What does it mean? First we need to allocate the inputs, and that will be new dense of samples count, labels count, and nil. Okay, then we go through all of the values. And what we're doing, we calculating the value that will be -1 multiplied by y and divided by the d values at j, and loss the input set and type in constant overflows. Yes, that should be float 64, but I'm doing the division anyway. And normalizing, so this is the calculation of gradient, then we normalize. We don't have to do another loop, because samples, it's in samples count. We can do it at once. I mean, I can write it here, like divide once again, but that's, you know, just easier to understand. So this should be the calculation for categorical cross entropy loss. Then the question, can I test it somehow? And I think I can. I mean the categorial loss backwards, and I'm thinking what should be the input, and d values, calculate the gradient, d values. So I think it's an activation to output, and here we need the target classes. Target classes. And print formatted categorical loss d and this is inside this one, so it's between accuracy and optimization. Well, there are some values. I'm not sure if they're correct, but actually it's -0. Looks like, well, we'll see when we'll test the whole thing, but okay, I assume that for now I implemented it correctly. I'm thinking, can I merge these two? Because here it's an allocation. Well, technically I can, right? I will leave it. But for example, if we check in, I mean, do I actually need to create? Because I'm creating the D inputs, I'm taking the sample count, I'm taking the label count. And then the question of this value. And I need to determine it, right? So value actually can be 0 at first, and then if j equals to, again, target I, then we assign value 1, then 0, 0, right? And then what we can do, we can do this. Oh, no. Wait. Yeah. And I don't need this whole thing. Right? Actually, I already declare it, so if we're on the target J value, let's try. That should be this one. I will. I think I should have something like this, right? Then kind of, because well, the weights are still random, so there could be some differences, but it looks very much the same. So this is what we can do, just in one pass. So there is no additional allocations. I mean, yeah, that's easier to understand here, but this is actually we kind of converting this into one one hot vector check, because if yes, okay, that basically it's, I mean, we'll see once we try to do all at once. Okay, I'm almost at the, well, actually more than the 50 minutes of recording. So what I did today, I implemented the categorical cross entropy loss, and the next one will be, I mean, if we take a look at the main, the one is missing is, we have the one is missing is actually this one, activation, it's softmax activation, and right, backwards. Good question what we need to do here, and I mean what will be the input values. But okay, the next time we will calculate the softmax activation derivative. There are more description about how it's calculated, I mean how to calculate the derivative. Then we'll have the function itself. Then I don't expect it to be that complex, although there are actually more things like tag of, we will have the inputs again. Okay, that sounds interesting. Okay, thank you for watching, and see you tomorrow. Bye bye.